So hello again. This is Roger Kochbar for the Bioelectricity course. We're in week 8, and this is lecture segment number 6. Here we're going to talk about strength duration curves. So if you look at the literature about stimulation, and certainly about the production of action potentials, all over the place you see people showing you strength duration curves or using the word strength duration. It's a very commonly used term. What are they talking about? We see it very clearly even in the simple geometry of a spherical cell. We found in the last segment that the equation for the transmembrane voltage as the result of a stimulus is this equation given on the top. If we take that equation, rearrange it, divide by R, we wind up with an equation with some new symbol names. That's the Weiss-Lapicque equation, which is this one down here. Now the Weiss-Lapicque equation addresses a particular question. The question that this equation answers is, how long does it take for a particular current to reach a threshold value? Now, the idea of a threshold value is that when you get Vm to a certain value, a threshold value, that value is good enough to lead to an action potential. That's only an approximation. It's not always true, but that is the idea of this equation. How long does it take to reach a threshold value? Or, phrasing it a little bit differently, how much current do I have to reach the threshold in a certain period of time? So if I phrase it that way, I'd say, how much current do I need to have to reach the threshold? That's here. Current required to reach the threshold within a certain period of time. And that period of time is here. So this is an equation that relates the time duration of stimulation, capital T, with the current required to reach the threshold in that time. The Weiss-Lapicque equation was, I believe, first written down as an experimental result rather than as a theoretical result. However, we get it easily and clearly as a theoretical result here in the case of a spherical cell. If we make a graph of what the Weiss-Lapicque result is telling us, then the graph is like this. Let's suppose that on the horizontal we put T, capital T, the duration. And let's suppose on the vertical graph we put ITH. What does the curve look like? Well, you may want to plot this for yourself, but I think the curve is going to look like this. And on the horizontal, this level, the minimum current required to reach the threshold, no matter how long the stimulus, this is what is called IR. And in the wonderful language that's been attached to these thoughts, this is called the Rho base, or HEOBASE, Rho base. The threshold current is the current that's required at a particular duration to reach the threshold voltage level. So all the points that are on this line reach the same threshold Vm. Sometimes people give this a different letter designation too, and they say that's VT, threshold value of VM. The remarkable thing about the curve is that it corresponds to two different important experimental findings. The first is there is a minimum level of stimulation that's required, or you'll never get there. The second is that the stimulus grows bigger and bigger as it gets shorter and shorter and shorter. So as the stimulus gets shorter, the current required gets greater and greater and greater, which poses a practical and theoretical limit on how short stimuli can be. There are lots of other factors that grow into this, and as stimuli get to be very short, one begins to understand that this theory really doesn't work very well, and there are a lot of counterexamples that are presented. On the other hand, it does work reasonably well across quite a range of durations, and thereby it has value in many contexts most of the time. Thank you for watching this segment. I like this picture at the end of this segment because of all the points and complications. That's actually what's true in a strength duration curve, a simple-looking curve, but there are a lot of points and complications. Thank you for watching.